Welcome to lesson number 2, reflection 1 from the section on light and sound. In this particular lesson, we're going to be looking at the laws of reflection. Lesson 2, part 1. Make sure you have your notes downloaded so you can do the class with me. Every student has some idea of what reflection is about. All waves undergo reflection. So you know when you look into a mirror, the light rays bounce back and you can see an image of yourself. When you shout at a building or a cliff face, you can hear the echo of your sound wave being reflected from that hard surface. So here's a simple definition of reflection, one that you'll easily remember. The bouncing of waves off an obstacle in their path is called reflection of waves. Let me have a look at the reflection of waves in a little bit more detail. Here I've got a reflector, some kind of surface that bounces the waves back. That reflector might be a mirror in the case of light. It might be some kind of hard surface in the case of sound. So I'm going to have a wave, show a wave coming in towards that reflector. So here's my wave. That wave there is called the incident wave. Do you know, it might be a little bit easier to actually show my wave just as a straight line. So here's a straight line going through the middle of that wave. We'll often draw the wave like that. There's my incident wave. Now I want to measure some angles. You might think I'll measure the angle to the reflector. But we actually don't do that. We actually measure it in respect to a line called a normal. A normal line in maths is a line perpendicular or at right angles to the reflector. So n represents my normal. So we're going to measure all angles with respect to the normal. Now, the angle the incident wave makes with the normal is called the angle of incidence. I'm going to represent that by little I. So that symbol there represents angle. So angle I, that is my angle of incidence. Now what happens then? Well, just think, if you fired a tennis ball at an obstacle, it'll be reflected out at the same angle it came in. So here's my reflected wave. Once again, to simplify the process, I might just represent it as a line representing the wave. It's easier to draw. There's my reflected wave. And the angle the reflected wave makes with the normal, that's called the angle of reflection. Angle or angle of reflection. Now, is there some kind of relationship between the angle of incidence and the angle of reflection? Well, common sense will tell you that they're equal. This has also been proved by experiment. So I can say that the angle of incidence is equal to the angle of reflection, and that's actually the first law of reflection. There's actually 2 parts to the laws of reflection. The first part is the angle I is equal to the angle R. Let me go back to my notes. Here's the definition for the laws of reflection. Number 1 tells me, as I've just said, that the angle of incidence is equal to the angle of reflection. That's a formula if you like. It's not in your table book, but it's so easy to remember. Angle I is equal to angle R. The way I know it's not in my table book, in my notes I haven't written down the page number in the table book there. So there's probably going to be 5, 6 formulae that are not in your table book that you have to be aware of. Now, what is the second law? Well, the second law is this. It says the incident wave, the reflected wave, and the normal at the point of incidence. The point of incidence is where they hit the reflector. All lie in the same plane. Well, what does that mean? It means if the incident wave comes in along your screen, then the reflected wave will bounce out along your screen. It won't jump out of your screen towards you or into your screen away from you. And the normal as well all lie in the same plane. So if they ask you for the laws of reflection, you need to give both parts. Let's have a look at example 1. So in example 1, a sound wave is emitted from S, travels down a pipe, and is reflected at O, then travels to OR, which is at the same height as S, that height being 80 meters. Find the time for the trip SOR, and they give me a constant that's not in the table book, and that is the speed of sound in air is 340 meters per second. Okay, so let me do that question. I've redrawn the diagram here. So let me write down the constant first of all. They're telling me that the speed of sound, which I call V, and that's equal to 340 meters per second. Well, the first thing to do is to use my law of reflection, and that is the angle of incidence, I, is equal to the angle of reflection, R. There's your incident wave coming in. There's the angle of incidence, 30 degrees. So obviously, this is the angle of reflection, and that's equal to the angle of incidence. So this is 30 degrees. I want to find the time it takes for that wave to go from S to O to OR. I'm going to find the distance OR, and then I can find the entire distance by doubling it, because that triangle on the left and that triangle on the right are congruent. That's a right angle triangle there. Let me have a look at it. Let me concentrate on this right angle triangle. I want to find the distance OR. I've got the angle 30 degrees. That represents the adjacent to 30 degrees, and that represents, OR represents the hypotenuse. So it sounds like cos to me. Cos 30 degrees is equal to the adjacent 80 divided by the distance OR, which I write down like this. I want to find OR, so slide the OR up and the cos 30 down. So OR is equal to 80 divided by cos 30 degrees. I'm going to put that into my calculator. So always have your calculator and your table book at hand. So 80 divided by cos 30. That will give me, say, to one decimal place, 92.4. And that's 92.4 meters. Well, what's the distance of the entire journey from S to O to OR? That distance SOR. Well, that distance will be twice OR. So multiply the answer in your calculator by 2. One decimal place, I get 184.8 meters. Now I'm going to use a formula that you used in a previous lesson. What's the formula for velocity in general? Velocity, V, or speed, is distance S divided by time. I'm looking for the time of the journey, so I'm going to slide the T up and the V down. So T is S over V. The distance is the distance SOR, which is 184.8, divided by the speed of sound, which is 340 meters per second. So I'm going to put that into my calculator. Fraction button, 184.8 divided by 340. And I get a time of 0.54 seconds. You can do 1 or 2 decimal places. I'll go for 2 here. So I get a time of 0.54 seconds. Okay. Finally, I want you to do some numerical problems. So if you go to the end of your chapter, you can see there's a selection of problems. So I always want you to practice. I don't want you to go on to the next lesson without having done the numerical problems, because that's just going to lead to problems later on down the road. You have to try and get all the stuff we've done today, which isn't very hard, but just get it nicely into your head. So I'm looking at numerical problems at the end of that chapter on lesson 2. We're going to do from 1 to 7. There's a nice selection of problems where you have to do a little bit of thinking, and they involve all the stuff you've done in this lesson and previous lessons. So we're gradually building up our knowledge. Okay, so that's the end of the lesson.